Imagine trying to map the entire universe, but you are only allowed to look through a tiny plastic drinking straw.
That sounds incredibly frustrating.
Right. You point it at the sky, you see this beautiful, highly detailed little speck of blackness with, I don't know, maybe a galaxy or two, and then you'd have to move the straw a fraction of an inch just to see the next speck.
Yeah, and for decades, that is essentially how humanity has explored the cosmos.
Exactly. Our greatest space observatories have given us these breathtaking ages, sure, but their field of view has always been incredibly narrow. But according to a newly released May 2026 report from Science Daily, that entire paradigm is about to be completely shattered.
Shattered is definitely the right word for it.
Yeah. NASA's preparing to open this massive panoramic floor-to-ceiling window on the universe. And today we're taking a deep dive into the source material to understand exactly how this is happening. We are talking about the Nancy Grace Roman Space Telescope. It's a mission that's about to fundamentally alter our understanding of dark matter, exoplanets, and really the very structure of the cosmos.
And, perhaps the most shocking part of this Science Daily report isn't even just the sheer scale of the science. I mean, it is the timeline.
Oh, yeah. Space missions and timelines. Usually not a great combo.
Exactly. The aerospace industry is notorious for staggering delays. Flagship missions typically run years, sometimes a full decade behind schedule. Budgets balloon, components fail testing, and launch dates just get pushed further and further into the future.
Right, James Webb being the classic example.
Yeah, exactly. Yet NASA just announced they are targeting a launch for the Roman Space Telescope as early as September 2026.
Wait, really? September 2026?
Yeah, they are actually moving the mission up from their previous commitment, which was, quote, no later than May 2027. Launching a multi-billion-dollar flagship space telescope nearly a year ahead of schedule is practically unheard of.
Okay, let's unpack this. Because anyone who actually follows space exploration knows that this kind of acceleration is the exception, not the rule. Like you mentioned with the James Webb Space Telescope, that was an engineering marvel, but it was also just a logistical nightmare that took decades to finally get on the launch pad.
Decades of nail-biting, yeah.
Right. So my immediate question is this September 2026 date just aggressive public relations from NASA to keep their funding secure? Or is there an actual mechanical reason why this telescope is coming together so much faster than its predecessors?
Well, what's fascinating here is that this accelerated timeline is the direct result of a massive structural shift in how we build and deploy space technology. The report includes a statement from NASA Administrator Jared Isaacman, and he points to this exact dynamic.
What did you say?
He calls Roman's development a true success story of what we can achieve when public investment, institutional expertise, and private enterprise come together to take on the near impossible mission.
Oh, public and private enterprise.
Yeah, because for decades, NASA was forced to essentially build the payload and custom design the launch vehicle procurement process almost in tandem. It was just a massive bottleneck.
That makes total sense.
Okay.
It would be like trying to design a revolutionary new scientific instrument, but also having to build the specific truck and then pave the specific road needed to transport it to the laboratory.
That is a brilliant way to frame it. Now let's look at the management of the Roman mission. You have the absolute titans of institutional science managing the instrument itself.
Right, the old guard.
Yeah, NASA's Goddard Space Flight Center, the Jet Propulsion Laboratory, Caltech's IPAC, and the Space Telescope Science Institute. I mean, these are hyper-meticulous organizations that spend decades perfecting a single lens or a single sensor array.
Which is exactly what you want when you're shooting a telescope into space.
Exactly. But instead of getting bogged down in the launch logistics this time, they are utilizing private enterprise. Specifically, a SpaceX Falcon Heavy rocket launching out of Complex 39A at the Kennedy Space Center.
Complex 39A, which is the same historic pad that launched Apollo to the moon and the space shuttles, right?
The very same, but now it operates with this rapid commercial cadence.
So they just buy a ticket on an existing rocket.
Right. SpaceX provides a reliable, off-the-shelf, heavy-lift delivery service. The infrastructure is already totally streamlined.
Yeah.
The institutional scientists don't have to worry about the rocket at all. They know the ride to space is already sitting in the driveway with the engine running.
Wow. I love that.
Yeah, that synergy, Marrying the bespoke, rigorous perfectionism of public science institutions with the sheer iterative speed and logistical muscle of private aerospace, that is what shaves a year off a launch date.
I mean, that is a paradigm shift for sure. But getting to the launch pad early doesn't mean much if the hardware in the cargo bay isn't revolutionary. And the hardware here is doing something we have never really attempted at this scale.
Oh, absolutely not.
Like, the Roman Space Telescope features a primary mirror that's 2.4 meters across, which, if I remember correctly, is roughly the same size as the mirror on the Hubble Space Telescope.
Yep, almost exactly the same size.
But here's the kicker. Roman's field of view is 100 times larger than Hubble's.
It is an absolute optical masterpiece. They took the light-gathering power of our greatest historical observatory and just stretched the canvas to an unbelievable degree.
100 times larger.
Yeah. And to capture that massive canvas, Roman is equipped with an incredibly powerful infrared imaging suite.
Okay, here's where it gets really interesting. Because the volume of information this telescope is going to beam back to Earth over its 5-year primary mission is borderline incomprehensible.
It's staggering.
The report states it will generate an archive of roughly 20,000 terabytes of data. And for you listening, 20,000 terabytes is a number that just kind of bounces off the human brain.
It really does. It's hard to visualize.
Right. So to visualize it, imagine a high-definition 4K movie. To hit 20,000 terabytes, you wouldn't just download a few movies. You would be downloading the equivalent of about 2 million 4K movies.
2 million.
Yeah. But the true challenge isn't just storing those movies. It is asking an algorithm to watch all 2 million of those 4K movies simultaneously, frame by frame, and flag the exact pixel where something in the background slightly changes color.
Which is just an insane data management challenge. The telemetry required to beam that much data down from orbit on a daily basis is a marvel in itself.
I can only imagine.
But we have to look at the type of light Roman is capturing to understand why the data is so incredibly rich. Because as we said, Roman operates primarily in the infrared spectrum.
Right. And I know infrared is heavily favored in modern astronomy. James Webb uses it too. But why is it the absolute linchpin for this specific wide field mission?
Well, space is incredibly dusty. Yeah, literally. There are massive, dense clouds of cosmic dust floating throughout our galaxy and beyond. So when you try to look at regions where new stars are forming, or when you try to look into the center of the Milky Way, that dust blocks visible light.
It just acts like a wall.
Exactly. The visible light hits the dust and just scatters. But infrared light has a longer wavelength. It physically slips past the dust particles.
Oh, wow.
Yeah, so instead of seeing a dark cloud, you see the actual heat signatures of the stars incubating inside it.
That's amazing. So it just cuts right through the fog.
It does. And furthermore, because the universe is expanding, light from the most distant ancient galaxies gets stretched out as it travels toward us. By the time it reaches Earth, that light has stretched so far that it actually drops out of the visible spectrum entirely and becomes infrared.
So infrared isn't just about piercing through the fog. It's actually about looking back in time to the oldest structures in the universe.
Yes. That is the dual power of the instrument. And if we connect this to the bigger picture, this combination of dust-piercing infrared vision, a massive panoramic field of view, and a 20,000 terabyte pipeline fundamentally shifts how astronomy even operates.
How so?
Well, historically, observing the cosmos was basically an artisanal process. An astronomer would write a proposal, beg for a few hours of telescope time, and then point the lens at one specific patch of sky to test one specific hypothesis.
You're requesting time to look through the drinking straw.
Yes, perfectly
Right.
said. Roman doesn't do that at all. Roman acts as a cosmic surveyor. It just sweeps across massive swaths of the sky, drinking in everything.
Just taking the whole picture.
Exactly. It builds the 20,000 terabyte archive first. Then the scientists simply log into the database from their laptops, whether they're at Caltech or a university in another country entirely, and they mine the data.
That's wild.
Yeah, you aren't competing for telescope time anymore. You are mining an existing, ever-growing digital replica of the universe.
Which is the ultimate data management dream for anyone who values efficiency. Like, this isn't information overload where you are just drowning in noise. This is pure, unprecedented signal.
Right.
But you don't build a 20,000 terabyte archive just to take beautiful panoramic photos for a textbook. You build it because the mysteries you're trying to solve require an almost absurd scale of evidence.
Yes, an absolutely massive sample size.
And that brings us to the actual scientific hit list. The phenomena Roman is designed to hunt down.
Right. And the source material highlights 3 primary targets for this: exoplanets, dark energy, and dark matter.
Okay.
And the numbers attached to these targets are just staggering. Roman is expected to investigate around 100,000 exoplanets. It will map hundreds of millions of galaxies, and it will observe literally billions of individual stars.
The report also specifically mentions a headline about how the telescope will catch, quote, 100,000 explosions to rewrite the story of the universe.
Yeah, those explosions are supernovae, specifically a type of exploding star that always detonates with the exact same baseline brightness.
Okay, why is that important?
Because we know their true brightness, we can calculate exactly how far away they are based on how dim they appear to us from Earth.
Oh, like a lighthouse.
Exactly like a lighthouse, they act as cosmic distance markers, or what astronomers call standard candles.
So what does this all mean? I mean, we've heard about dark matter for years. We know exoplanets exist. Previous telescopes have found thousands of them. What makes Roman's approach to finding these things fundamentally different from the great observatories of the past?
This raises an important question, and the distinction here is super vital. It comes down to the immense power of statistics. So let's look at exoplanets first.
Okay.
A decade ago, discovering a single planet orbiting another star was front-page news. It was an anecdote. It proved that our solar system wasn't a total fluke.
Right, like, oh, look, we found one.
Yeah, exactly. But discovering one or two, or even a few thousand exoplanets doesn't give you the full picture of planetary evolution.
Because it's a biased sample size. Like, if you only look at one neighborhood, you don't understand the demographics of the entire planet.
That is the perfect analogy. Roman is moving us from anecdotes to demographics. By identifying 100,000 exoplanets, we can finally conduct a true cosmic census.
A cosmic census?
Yeah. Scientists will be able to map out exactly how common Earth-sized planets are in the habitable zones of their stars. They can determine if gas giants usually form close to their suns or far away, and Roman finds them using a technique called microlensing, which is completely reliant on its massive field of view.
Okay, so how does microlensing work in practice?
Well, it relies on gravity. If a star passes directly in front of a background star from our perspective here on Earth, the gravity of the foreground star acts like a magnifying glass.
It bends the light.
Exactly. It briefly brightens the background star's light. Now, if that foreground star happens to have a planet orbiting it, that planet's gravity creates a tiny secondary blip of magnification. Right. But to catch that alignment, you have to stare at hundreds of millions of stars simultaneously for long periods, just waiting for the exact moment they cross paths. Hubble could never stare at that many stars at once.
But Roman can.
Roman can.
It is a brilliant mechanism. We are literally using the very fabric of space-time as a magnifying glass. And that same principle of gravity bending light seems to be how Roman is going to tackle the biggest mystery of all, which is dark matter.
Oh, yeah. Dark matter is the ultimate ghost of the universe.
The ghost.
Yeah, because it makes up roughly 85% of the mass in the cosmos, yet it doesn't emit light, it doesn't reflect light, and it doesn't block light. It is completely invisible.
So how do we even know it's there?
The only reason we know it exists is because its gravity holds galaxies together. If dark matter weren't there, galaxies would literally spin themselves apart.
Okay, but if it is completely invisible, how do you map it?
Well, you don't look for the dark matter itself, you look for the distortion it leaves behind.
Okay, give me an analogy.
All right, think of space-time as a mattress. If you place a heavy, invisible bowling ball on a mattress, you obviously can't see the ball, but you can see the fabric of the mattress dipping downward.
Right.
In space, massive clumps of invisible dark matter warp the space around them. When the light from a distant galaxy travels through that warped space to reach us, the shape of the galaxy actually appears slightly stretched or smeared.
Oh, so it's like looking at a distant street lamp through warped pane of glass. You know, the glass is there because the light looks distorted.
Exactly. We call that weak gravitational lensing, but the distortion is incredibly subtle.
Like barely noticeable.
Right. If you just look at one galaxy, you can't tell if it is actually warped by dark matter or if it was just born a little lopsided.
So again, you need a massive sample size.
Precisely. The only way to prove the presence of dark matter is to measure the shapes of hundreds of millions of galaxies and look for a collective statistical pattern in how their light is stretched.
And Roman can do that.
Roman will execute this weak lensing survey on a scale that is simply unprecedented. By mapping where the dark matter is, we can reverse engineer how the universe clumped together right after the Big Bang.
And while Roman is mapping these hundreds of millions of galaxies and watching billions of stars waiting for 100,000 supernovae to explode, it's also doing something else. The report points out that because of this wide net, astronomers fully expect Roman to capture unusual cosmic events and phenomena that humanity has literally never witnessed before.
And honestly, that might be the most thrilling aspect of the entire mission.
Just a complete unknown.
Yeah. When you survey the universe at this scale, with this level of sensitivity, anomalies are essentially guaranteed. We are going to find things that currently do not exist in our physics textbooks.
Like what?
Who knows? Bizarre stellar behaviors, inexplicable flashes of energy, structures that completely challenge our current models of the universe.
It is the ultimate scientific payoff. You build an instrument to answer 3 specific questions about dark matter, dark energy, and exoplanets. But the real prize is discovering questions you didn't even know you should be asking.
Yes. And returning to our starting point, this is exactly why the September 2026 launch date is so consequential. That public-private logistical synergy we discussed earlier isn't just saving NASA money.
It's buying us time.
Exactly. It is accelerating our access to these fundamental truths. Every month that we move this launch forward is another month of data pouring into that 20,000 terabyte archive.
All right, so let's do a rapid recap of what we've covered today. So when you, the listener, see this mission trending in the news, you know exactly what is happening beneath the headlines.
Sounds good.
First, the timeline and the logistics. NASA is aggressively targeting a September 2026 launch for the Nancy Grace Roman Space Telescope, flying on a SpaceX Falcon Heavy. This early launch basically proves that a new paradigm is working. They're allowing commercial aerospace to handle the heavy lift logistics so that institutions like Goddard and JPL can focus entirely on perfecting the scientific instruments.
Right. And second, the technology itself. The payload is a panoramic window into the infrared universe. It takes the resolution of Hubble, multiplies the field of view by 100, and uses infrared wavelengths to pierce through cosmic dust and look back at the oldest structures in existence. It will generate a staggering 20,000 terabyte database, which essentially shifts astronomy from an observational science to a data mining science.
And third, the science. Roman is going to leverage the sheer power of statistics to hunt the invisible. So by utilizing gravitational lensing, it will measure the distortions of hundreds of millions of galaxies to map dark matter. By monitoring billions of stars, it will catch 100,000 supernovae to track the expansion of the universe. And by utilizing microlensing, it will execute a cosmic census of 100,000 exoplanets to finally understand the true demographics of solar systems out there in the dark.
It is a machine perfectly designed to take the measure of the universe on a macro scale, while remaining sensitive enough to catch the anomalies that will redefine our physics.
So you are now completely prepped. You know why the Roman Space Telescope matters, the mechanisms of how it works, and exactly what is at stake when it reaches orbit.
Yeah.
But there is one final, somewhat mind-bending implication to all of this that builds directly on what we've discussed today. Yeah.
Oh, wow.
We talked about the sheer, unyielding volume of information this telescope is going to provide, right? 20,000 terabytes of panoramic deep space data, billions of stars, hundreds of millions of galaxies.
It's a data set so dense that human astronomers could spend 1,000 lifetimes looking at the images and still only scratch the surface.
Exactly. And that leads to a really profound question. If the scale of this archive far exceeds the capacity of the human eye and the human brain to process, who's actually going to be doing the discovering?
Oh, wow. That's a great point.
Right. Could it be that the most paradigm-shattering breakthroughs hidden within the Roman Space Telescope's data, the anomalies we don't even have names for yet, will ultimately be found not by a human astronomer looking at a screen, but by future artificial intelligence algorithms?
Yeah, algorithms specifically designed to comb through 20,000 terabytes of darkness, just recognizing cosmic patterns and subtle distortions that human minds cannot even comprehend.
Exactly. Because when you build an instrument that outpaces human perception, you really have to wonder what kind of intelligence will be the first to truly understand what it finds.
That is something to think about.
We'll leave you to mull that over the next time you look up at the night sky.